Today we're going to solve the problem. Let C of t equal x of t, y of t be a plane curve. Show the curvature is equal to this expression, x dot y double dot minus x double dot y dot divided by the norm of the tangent vector, x dot squared plus y dot squared to the power 1/2 raised to the power 3. Okay, so let me just note a couple things. First of all, we know that that if gamma of s from say 0L into the plane is a unit speed, then we know that the curvature of gamma is, well, if gamma of s is like gamma of s is x of s, y of s, then the curvature is going to be, by definition, the inner product of the tangent vector gamma prime of s with, the acceleration gamma double prime of s, inner product of the acceleration with the rotated tangent vector r pi halves gamma prime of s. Okay, and this is because the tangent vector is unit speed, so it's not changing its magnitude, it's not changing its length. Therefore, the acceleration is always orthogonal to the direction of the tangent vector. Therefore, the acceleration is always in the direction of the tangent vector rotated by pi halves, and then we're defining the curvature to be the magnitude of the acceleration, and it's assigned magnitude with positive sign in the direction of this normal vector to the curve, and negative curvature if it's against the direction of the normal vector to this curve. So again, we have a picture here, curve gamma. We have a tangent vector gamma prime, which is always of unit norm by assumption, unit speed. So gamma prime always has a length of 1. And then I rotate this by pi halves counterclockwise, and that gives me this normal vector n hat, which is here. Here's n hat. And then the acceleration we know is a second derivative of this gamma prime. Since gamma prime is a constant length, it's only changing in the direction orthogonal to itself. And so gamma double prime must be in the direction of n, and then we're defining the curvature to be the magnitude in the direction of n. So for instance, if I have a curve which curves inward towards the normal vector, okay, so here's gamma prime of s. If I curve toward the normal vector, then that's positive curvature. And of course, the magnitude will tell me how quickly I'm curving in this direction n. And then if I curve away from the normal vector, then that's negative curvature by this convention, okay? All right, so we showed in the previous problem, we're just going to do it quickly again, that this curvature has a very specific form. So gamma double prime is just x double prime, y double prime. Now notice the primes are derivatives with respect to s, and s is the arc length parameterization, or the unit speed parameterization. So prime derivatives are derivatives with respect to s, and dot derivatives here are derivatives with respect to t. And then here we rotate this, so we take a rotation by pi over 2 counterclockwise, that's this matrix here, and we rotate the vector gamma prime, which is just x prime, y prime. Okay, so what this gives us is, it should give us, x prime, y double prime minus x double prime, y prime, okay? So this is the curvature of a unit speed geodesic, and note that unit speed x dot squared plus y dot squared is going to be 1, if this curve is parameterized unit speed. So this actually directly agrees with this result. Okay. But now let's prove the theorem in general. So first of all, we'll note that this curve C, it admits a unit speed reparametrization. Okay. So T is in the interval AB, and if we define S of T to be the integral from A to T of C prime of T dt. I should use maybe C here, just because I'm using T in the bound of the integral. So this is going to be the arc length of the curve from the cumulative arc length from A to T. Okay, and so for example, S of B is equal to L, which is the total length of the curve. Okay, this is some sort of cumulative length of the curve from A to T. Now, this actually gives us, if this C prime of C is never zero. Okay, so if this curve C of T has positive speed everywhere, which note that it has to have positive speed in order for this to be well defined. So, right, if the speed vanishes, then we're going to have that this expression is going to vanish to zero, and so the curvature won't be well defined. And so, of course, that's a little bit hand wavy because the numerator might also vanish. But just for the simplicity of the sake of argument, we're going to assume that this C prime, the speed of the curve, is never zero. And so in this case, we know that S prime of T, okay, or sorry, S dot, ds over d over dt, okay? This is just, by the fundamental theorem of calculus, this is just the norm of C prime of T, and this is always positive, which means that this arc length, what's called an arc length reparametrization, has an inverse, okay, by the inverse function theorem, because its differential is always going to be injective, okay, so the derivative is non-vanishing, and therefore we can find an inverse which is smooth. We can find an inverse parametrization T of S, which is a function from 0L, which is the interval used for the arc length parametrization, into AB, and this is a smooth inverse of S of T. And the property that it's going to satisfy is that C of T of S is a unit speed. And this is what's called the arc length parametrization. So once we know that this arc length reparametrization exists, we can then use the arc length reparametrization, and we know that the curvature of this reparametrized curve, okay? So we know that the curvature is going to be x prime, I believe. Let's see. Yeah, x prime y double prime minus x double prime y prime And now these are primes are with derivatives with respect to s, the arc length parameterization. And so then if we calculate y, let's calculate y double prime real quick. So we have d over ds of dy of t of s ds, okay? So this is the second, so this is y double prime. I'm just taking two derivatives with respect to s, the arc length parameterization, of y of t of s, okay? And then by the chain rule here, okay, so first we're going to evaluate this expression in terms of the chain rule. This is d over ds of y dot, so dy over dt, dt over ds, okay? So that's just by the chain rule here. And then we're going to evaluate this expression, okay? So this expression, I'm going to take the derivative of the first, okay? And the derivative of the first is just d squared y over dt squared dt over ds, okay? So this is the derivative of dy over dt with respect to s, and then I've used the chain rule here to evaluate it, okay? And then I multiply this by dt over, by the second, so dt over ds. So then I'm going to end up with a dt over ds squared here. And then I have the derivative hitting on the second factor. So I have a dy over dt, and then a d squared t over ds squared, okay? Wonderful. Okay. So let's write it in terms of our dots. So this is y double dot, and then dt over ds squared plus y dot d squared t over ds squared. Okay. So, and then similarly, so this is our expression for y double prime. And then similarly, x double prime is going to be x double dot, so second time derivative of x, dt over ds squared plus x dot d squared t over ds squared, okay? All right, and now x prime, okay, let's just quickly note x prime, this is dx over ds, which by the chain rule is dx over dt times dt over ds. And similarly, y prime is y dot, so dy over dt, dt over ds, okay? Great. So let's plug this into our curvature formula. Okay, so we have x dot dt over ds, y double prime, y double dot dt over ds squared plus y dot d squared t ds squared minus y dot dt over ds multiplied by x double dot dt ds squared plus x dot d squared t ds squared. Wonderful. And now if we look at the terms which are the x dot single dot terms, okay, so this term here I have an x dot dt over ds, y dot d squared t over ds squared, minus a y dot dt over ds, x dot d squared t over ds squared. So these terms cancel, okay? these two terms cancel, and I'm just left with an x dot y double dot minus y dot x double dot multiplied by dt over ds cubed, okay? All right, so what is dt over ds? Well, recall that t of s, by the inverse function theorem, okay, dt over ds, okay, so this is going to be 1 over 1 over ds over dt. This is the inverse function theorem, okay? So, and we've assumed the speed is non-vanishing. Okay, and ds over dt, remember s of t was this integral, this cumulative arc length, c prime of c, or c dot, excuse me, c dot of c dc. And so this is just, so s prime, or s dot, ds over dt, by the fundamental theorem of calculus, the derivative of this cumulative integral is just the integrand evaluated at the endpoint, which is varying, namely the upper endpoint in this case. And so this is just going to be the norm of c dot of t. Well, this is just, we know what c dot is, it's x dot y dot. So this is just the square root of x dot squared plus y dot squared. Okay, so then by the inverse function theorem, this dt over ds is just 1 over square root of x dot squared plus y dot squared. Okay? And so that gives us our expression, because then we just plug that in for dt over ds and we get x dot y double dot y dot x double dot divided by x dot squared plus y dot squared to the 3/2. Okay.